Okay, welcome back. So in this video, we'll do a one-way between subjects ANOVA and jamovi. I made everything bigger in Windows to hopefully make it a little bit easier to see on your end. Um, so hopefully doesn't get too distracting. So what we're looking at here, this is data from Module 8, if you're in my class, that you used in your homework assignment and or the practice exercises rather. And so we're going to look at this for the sake of our ANOVA, and I also added one variable that I'll get to in a little bit. So first, let's start with the basics of how to do an ANOVA. So go to Analyses, ANOVA. I believe this comes standard. You could do one-way ANOVA, but I prefer to just click on ANOVA because that gives you a little bit more freedom as we come back to it in other analyses. And so let's do, well, first we'll see dependent variable and fixed factors. Fixed factors, think independent variables, right? So our dv, it's always going to be our dv. So let's say, for example, in this one, I wanted to go back and see if overall GPA differed across years, right? So first year, second year, so on and so forth. So in that case, overall GPA is going to be our dv. Year is going to be our fixed factor. And we can see here right off the bat that we don't have a significant ANOVA statistic, right? We don't have a significant f-test. Our f is barely above 1, and our p is obviously not significant, right? And so in that case, we don't need to go any further. So let's say I wanted to, or for the sake of our example, if we want to see a significant f-test, I added some data about academic self-efficacy. So these are students' beliefs and convictions that they can successfully perform academic tasks. So if someone's really high in academic self-efficacy, they feel like this sense of conviction that they can essentially do what they need to do when it comes to academics. Someone low in that then doesn't feel like they can. And so let's look at that across years. And before I click it over, we can probably assume that the further we go in school, the higher our self efficacy is going to be about school because we just get experience, and through that experience comes confidence. And if we run our tests, wow, huge F test, right? Or huge F statistic. Obviously significant. That's honestly the largest F I've ever seen in my personal experience. So this data is obviously fake, but I wanted something that clearly shows significance here. And so you'll see here, there are a couple of different things we can do. There's just a lot more to this analysis than previous analyses. And so for starters, we can toss in effect size. So we can do eta squared and omega squared. Actually, let me get rid of that. Um, yeah, so eta squared, omega squared. Yeah, despite the fact that omega squared is more conservative, you can see there's still both around 0.45. So about 45% of the variance in academic self-efficacy can be explained by year in school. Year was 1 to 4, ranging from first year at college to 4+ years at college. So obviously it's a huge effect. So we wanted to do post hoc tests. We come down here and we can just move year over, or I guess before we do that, we already have Tukey selected, so we're good there. Move year over, and then it kicks out post hoc tests. And so we can compare these here. So our comparison, or actually let's label a year first. Let me pause it and clean this up. Okay, so you can see that now we have labels instead of numbers. So here we can see for each of these comparisons, we're subtracting, just like we did in our by hand or handwritten ANOVA post hoc comparisons. We're making basic comparisons between these groups, right? Because a significant ANOVA overall is simply telling us that there's an overall significant test, but it doesn't tell us where those differences lie or where those significant differences lie. And so we do this post hoc test to analyze the specific comparisons. And so for this first one, you can see we're taking freshman minus sophomore, and we have a negative mean difference. So that means that sophomore self-efficacy is higher than freshman self-efficacy. Then we have our t statistic and our p-value. And so if we look at that, we can see everything significant except for this last one, comparing juniors and seniors. So junior minus senior is minus 0.353. So that tells me that seniors do have higher self-efficacy than juniors, but that mean difference was not significant. right? And you can see just by looking at the mean difference column that the other mean differences were much higher. Some, like freshman to senior, is 2.1. So it's a huge difference on this 5-point scale. Junior to senior, not as big, and therefore it's just simply not significant. And let's see here. Where can I add the actual means? I guess I could do that real quick. If you want to just to like have those handy variables, academic self-efficacy split by, so you can see our actual means for each of those groups. So yeah, you can see some numbers to give a little bit more context to these. So that's one thing you can do to help you out. But I want to go back here, and I want to, let's say I also want to plot this, right? So I want to plot just to help me understand these mean differences a little bit more. If we go to estimated marginal means, we drag that over, then this is essentially giving us those estimated means for each group. And so you can see here very clearly that seniors have the highest, freshmen have the lowest. Our y-axis here is academic self-efficacy. And it kind of makes sense then, right? You can see more substantial differences between these three groups than between juniors and seniors, right? And again, that was our non-significant comparison. We can play around with this a bit more. We could add a marginal means table if we wanted that. So there you can see our estimated marginal means, right? Basically identical to those down there. Standard error, confidence intervals. Here our error bars are confidence intervals. Maybe we can make them standard error. You can see that kind of tightens it up a little bit. We can add our observed scores if we want that. That kind of muddies it up, right? So I encourage you to play around with that. Yeah, and that's really, I think, the main gist of what I wanted to go over here. There's more things we could do, like we could change our types of sum of squares. That's more advanced than we need to get into here. We could do assumptions tests, like homogeneity tests, if we wanted to. But again, for the sake of this, I just wanted to give you a basic rundown. And I guess one thing I hadn't done, if we want to compare that to a basic one-way ANOVA, here we're going to assume equal variances. And if we do this again, we had that as our dependent variable, year as our grouping variable. So you can see here, this just gives us a lot less, and that's why I like the other one. This can give us descriptive plots, right? It gives us less freedom over what that plot looks like. We can do post hoc tests. So we see those down here. So slightly different ways of arriving at the same result. But like I said, overall, I like just using the ANOVA function because it gives us just a little bit more flexibility and freedom over how we do it. So yeah, hopefully this was helpful. We'll see you in the next one.